Okay, last section of the chapter is 7.6. It's linear programming. In linear programming, we're going to try to optimize a set of restraints. So optimization is a process to find the minimum or maximum value of a quantity within given restraints. In a linear programming problem, a system of linear inequalities are the constraints. So for example, these are the constraints. The objective function gives the quantity to be maximized or minimized within the feasible or shaded region. So for example, when it gives you a function to maximize in a word problem, they might have you try to maximize the profit or minimize the cost or something like that. If there is an optimal solution, it must occur at one of the vertices of the feasible region. Okay, so for example, 1, 2, and 3, we're just going to practice graphing it and optimizing it without having it also be a word problem. Okay, now let's see. The first two constraints are x is greater than or equal to 0 and y is greater than or equal to 0, which is kind of nice because that means I'm in quadrant 1. Which is often the case because if we're doing real life word problems, we don't have many negatives in real life. Okay, I'm going to go ahead and graph. Okay, I'm not really going to graph them because they're on the axis. I'm just going to remember I'm in quadrant 1. Okay, I'm going to go ahead and graph the next one. I think I'm going to use slope-intercept form. But you could also use intercepts. They look fairly easy on this one. Minus x plus 6. Okay, so less than or equal, so it's a solid line. Down 1 over 3. I'm going to go down 1 over 3 again because I am not good at drawing straight lines on this thing. Okay, so I'm in quadrant 1 and I'm also less than or equal to this boundary line, so I should be lower. So I'm probably down here somewhere in this little triangle region. Let me go ahead and graph the last one. Okay, let's see. Negative y is less than or equal to negative 2x plus 5. I'm going to divide by negative, so the inequality is going to switch directions. This is a solid line. 1, 2, 3, 4, 5. The y-intercept is negative 5. I'm going to go up 2 over 1. My graph doesn't really have to be perfect because we're going to calculate all the vertices algebraically. But it's nice if it's kind of right, so you can kind of see if your answer looks right. Okay, this is greater than or equal to, so it should be above the boundary line, which puts it up here on this side. Okay, so if I stay in quadrant 1, and I am below the blue line and above the pink line, it looks like this is my feasible region, this quadrilateral. Okay, if there is a maximum or a minimum to this problem, it must occur at one of the vertices of the solution region. So it could occur here, 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 or here. So I'm going to list all those vertices. I'm going to list 0, 0 first. You don't have to show work for 0 to 0, but I got it from x equals 0, y equals 0. So if it's given like x equals 0, y equals 0, you don't show work, but I am going to show work for every single other one. Okay, let's go down to, let me do this point first, or next. Let's see, this is the line y equals 0, along with the pink line. The pink line is 2x minus 0 equals 5, or 2x minus y equals 5. I'm going to plug in 0, so 2x minus 0 equals 5. 2x equals 5. I did x equals 5 halves. So my vertex here is going to be, I don't have space, 5 over 2 comma 0. And that seems kind of reasonable. Okay, let me go up on the y-axis to this one. Okay, that's the x equals 0 line. And that's the x plus 3y equals 6 line. Although I think I'm going to use the slope-intercept form. Because if I do y equals negative 1/3 x plus 2, I just get y equals 0 plus 2 when I plug in 0. So this is 0, comma 2. Okay, and then my fourth vertex is way over here, and that's where the blue line and the pink line intersect. And I could use the slope-intercept form, or I could use the y-intercept form, or the standard form, sorry. I'm going to use a combination. I'm going to use x plus 3y equals 6, and then I'm going to use y equals 2x minus 5, so I could do substitution. Okay, so I got x equals 3, which looks correct with my graph, and then y equals 2 times x minus 5. 6 minus 5 is 1. So this last ordered pair looks like 3, 1. Okay, I have all 4 vertices listed, and I'm going to list them even though I'm very confident that the maximum is not going to occur at 0, 0. Okay, so I'm trying to maximize this function right here, the z equals 2x plus 7y. So I'm just going to plug them in and see which ordered pair produces the highest value. And list all the values so I can see that you did actually compare all of them. You don't have to show the plugging in step, but you do need to show that z equals 5 at 5 halves, comma 0. So 6 plus 7 is 13. Okay, because I'm maximizing, I'm looking for the highest value. So the highest value is 14. So for this problem, what is it asking? Find the maximum value. The max value is 14. Okay, if they only ask me for the maximum value, I'd be done. They often ask you where it occurs, and I would say it occurs at 0, 2. And I would have showed all my work to support my answer. Okay, let's try example 2. I'm just trying to show you different kinds of regions so you see each type of answer we might get. The constraints are here, and it says find the minimum and the maximum value, though the method is going to be exactly the same. Okay, it tells me x is greater than or equal to 0 and y is greater than or equal to 0, which is really just telling me quadrant 1 again. So I'm just going to keep in mind that I'm in quadrant 1. Then I'm going to go ahead and graph the next constraint. X plus y is greater or equal to 7. I could do intercepts, or I could do slope-intercept form. Y-intercept is 7, 1, 2, 3, 4, 5, 6, 7. The slope is down 1 over 1. Your graph doesn't have to be perfect, but it does help with your vertices if it's on the nicer side. This is greater or equal to the boundary line, which means I'm above the line somehow. You don't have to mark it, just keep in mind I'm going above the red line. Okay, if I had done y-intercepts, which I am going to do soon, if I plug in 0 for y, I would have an x-intercept of 7, which is down here. If I plug in 0 for x, I would have a y-intercept of 7, which would be here, and I could just connect the points that way. Okay, let me go ahead and graph the last constraint. Y-intercept is 5, 1, 2, 3, 4, 5. Down 3 over 5, 1, 2, 3, 4, 5. I'm going to go again. 1, 2, 3, 1, 2, 3, 4, 5. Is this solid? This is solid. Okay, let's see. I am greater than, so I want to be above the purple line. And I also want to stay in quadrant 1. Okay, if I had tried to do intercepts on this one, which I could have done, if I plug in 0 for the x, I get a y-intercept of 5, which is nice. If I plug in 0 for the y, I get an x-intercept of 25 over 3, which is 8 1/3. 1, 2, 3, 4, 5. And I could have gotten an okay graph from there. Okay, let me look for my feasible region. Let's see, I have to stay in quadrant 1. I have to stay above the red line and the purple line, which means I'm up in this infinite area. But I still have to be careful to stay in quadrant 1, so I'm not going to cross the x or the y axis. So this infinite area that extends forever is actually my solution region. Okay, when I consider the vertices of my solution region, there's a vertex here. There's one here, and there's also one here. I'm guessing, and because this goes to infinity, there's no maximum value. There is no maximum value. If I'm trying to maximize that function, I can always find a point that is bigger and bigger and bigger off in infinity land that'll make this a higher value. Because it's infinite in the positive direction, there's no maximum value. So I'm still going to find the minimum value, and I'm still going to specify that there was no maximum value. Okay, so let me look for my vertices. There's 3 of them. Okay, so I have this one up here, and that's at x equals 0. X equals 0, and then the red line I could use in slope-intercept form or in standard form. I have x plus y equals 7. So if I plug in 0, y is 7. So this is 0, comma 7, which seems reasonable. Okay, and then along the x-axis, I have y equals 0, and then I have the purple line, which I could use in standard form, or I could use it in slope-intercept form. Okay, if I plug in 0, I get 3x plus 0 equals 25, so x equals 25 over 3. So this is 25 over 3, comma 0. Okay, and then my third vertex occurs where the red and purple lines intersect. And again, slope-intercept or standard form, depending on whether you prefer elimination or substitution, probably. Okay, so I got y equals 2, and then I am going to plug it into x plus y equals 7. So x plus 2 equals 7, x equals 5. I should have left more space. So 5, comma 2, which does look realistic on my graph. Okay, now I already established there's no maximum value because this is infinitely unbounded, but I'm still going to try to maximize the z function. So z equals 3 times x plus 7 times 7. So z is 49 at 0, 7. It's 25 at 25 thirds, comma 0. And then 15 plus 14 is 29. Okay, so the minimum value is 25. So the minimum value is 25. If they ask you where it occurs, you would say at 25 over 3, comma 0. If they don't ask you, you would just say 25. Okay, one more example before we start adding word problems to this. And this is just to show you another representation of a maximum value depending on the outcome. Okay, let's see. So first it tells me 0 is less than or equal to x is less than or equal to 5. So I am going to actually graph this. Okay, so 0 is less than or equal to x. Should be solid. 1, 2, 3, 4, 5. So I have to stay between x equals 0 and x equals 5, including the boundary lines. Okay, now it tells me 0 is less than or equal to y is less than or equal to 4. So I have to stay between y equals 0 and y equals, oops, that's y equals 3. Y equals 4. 1, 2, 3, 4. Okay, so now I'm looking at this rectangular region right now. Okay, now I'm going to add in x plus y equals 6. Now I'm going to graph x plus y equals 6 using its intercepts. And that's because if I plug in 0 for y, I get x equals 6. 1, 2, 3, 4, 5, 6. So there's an x-intercept at 6. If I plug in 0 for the x value, I get y equals 6. 1, 2, 3, 4, 5, 6, which is up here. Okay, this is a solid line. Now, if you choose to use intercepts rather than slope-intercept form, that's fine, but you have to be a little careful on your shading. You might need to check a point. So if I plugged in 0, 0 is less than or equal to 6, that checks, which means I must be shading on this side of the line, which means my solution region is going to be in this area here. Okay, and this means I have a lot of vertices. Okay, luckily most of them don't require work because this vertex is 0, 0. And because that came from x equals 0, y equals 0, you don't have to show work. Okay, this vertex here is from x equals 5, y equals 0. This vertex up here is from x equals 0, y equals 4. But this vertex I'm going to show work for. So that's from x equals 5, and then from the last line, x plus y equals 6. So is that it? Oh, I guess it should have been at 5, 1. Okay, and then this one up here is at y equals 4 and x plus y equals 6. So this should be at 2, 4, even though my graph's a little off. I don't mind your graph being off because you're going to show your work. And then it won't matter. So 0, 4, 2, 4, 5, 1, 5, 0. Okay, I'm trying to find the maximum value here. Okay, I told you you don't have to show the plugging in work, but you need to show what it equals to. So 2 times 0 plus 2 times 0 is 0. 2 times 0 plus 2 times 4 is 8. 2 times 2 is 4. 2 times 4 is 8. 4 plus 8 is 12. 2 times 5 is 10. 2 times 1 is 2. 2 times 5 is 10. So I got 0, 8, 12, 12, and 10. Now I'm looking for the maximum value, but I got 2 maximum values, which doesn't totally make sense, but it kind of does. Okay, so the way I'm going to say that is that I know the max value is 12. Okay, but where that occurs, it actually occurs on the line segment from 2, 4 to 5, 1. I'm going to show you on the graph where this is. Okay, so what did I just say? So on the line segment from 2, 4, this is 2, 4, this is 5, 1. So every single point along this line segment will actually give you a maximum value of 12. Okay, this occurs occasionally. It actually occurs when the line you're trying to optimize is parallel to one of the lines that is a boundary of your region. Okay, now we're going to do a word problem. Okay, I might show you 2, I haven't decided, but in class we're just going to do 1. Okay, so for example 4, it says a company makes 2 models of GPS navigators at costs of $250 and $400. The $250 model yields a profit of $45, and a $400 model yields a profit of $50. Our merchant who sells the GPS navigators estimates that the monthly demand will not exceed 250 units. The merchant does not want to invest more than $70,000 in inventory for these products. Find the number of units that should be stocked to maximize profit. Okay, now the first thing it is asking me for is to define the variables, meaning which one do you want to make X or Y? And there's no right way to pick X or Y, it's up to you. But if you look at the question, it normally tells you what you're trying to find. I'm trying to find the number of units that should be stocked to maximize the profit. So X and Y are both going to be the number of units, but then I just have to remember the units of what? Okay, so what are they making? They're making 2 models of GPS navigators. One costs $250 and one costs $450. So the units of the $250 model and the units of the $400 model. And normally the question will tell you what two variables to set this up. Okay, B, I'm going to write the inequalities representing the constraints. So they're telling me any limitations. Okay, 250 model yields a profit of 45, 400 yields a month. The merchant who sells the GPS navigators estimates monthly demand will not exceed 250. Okay, will not exceed sounds like an inequality. Okay, will not exceed means it will not be higher than. If it's not higher than, then it could be less than or equal to. Okay, so what do I have? I have the units of $250 model plus the units of the other model will not exceed 250 units. Okay, I'm going to look for another inequality because one is not going to be enough. Okay, the merchant does not want to invest more than 70,000 in inventory. Okay, so that sounds like an inequality. Okay, it says not more than 70,000. So if it's not more than 70,000, it can't be more than, it could be less than or equal to. Okay, but this is money. So let me go back and see the money for each one. Okay, so for Model X, how much does that cost? Oh, it's 250 because it's the $250 model. So 250X plus the $400 model costs $400. Okay, it's also true that X is less than or equal to 0 and X is greater than or equal to 0 and Y is greater than or equal to 0 just for the sake of keeping everything positive. You don't have to list that, but you do need to respect that on your graph. Okay, next I'm going to write the objective function. And in this case, they tell me the objective function has to do with profit. So I can call it Z if you would like to. I'm going to call it P. Okay, so where does it tell me the profit? Okay, the 250 model yields a profit of 45. So for each X unit, it makes 45. The $400 model yields a profit of 50. Okay, now I'm going to sketch a graph, list the vertices, and determine which produces the maximum monthly profit. Okay, I'm just going to do a sketch. You are welcome to do the same. Okay, because X and Y are positive or greater or equal to 0, I'm not even going to sketch any quadrant other than 1. Okay, now I am going to graph this using intercepts, and I'm going to make a sketch, so it's not going to be perfect. Okay, so if I graph this pink function, if I do the intercepts on this, if I plug in 0 for y, I get x equals 250. Since my graph has no scale, I'm just going to put 250, 0 here. Label it if you're using intercepts so I can see what point it is, especially when I have no scale. Okay, for the y-intercept, if I plug in 0 for the x, I get y equals 250. And again, I have no idea where this is, so I'm just going to estimate that it's about the same as the other side, but I am going to label it. Okay, now I'm going to draw the line. Okay, and I'm going to keep in mind this is less than or equal to, it is lower than. If I plug in 0, 0, that checks, which also tells me it's going to be lower than. So I'm looking at this triangle region. Okay, I'm going to go ahead and graph the next one. I'm going to use intercepts again. And I'm going to do it without showing work, and you can too. Okay, so if I want the x-intercept, I'm going to plug in 0 for y. So I'm going to have 250x equals 70,000. 70,000, I'm going to get my calculator, divided by 250, is 280. So x-intercept is 280. I don't know where that is, but it's past 250, so I'm going to put it right here. I'm just trying to get a sketch of my graph so I kind of can see where the points of intersection are going to be. For the y-intercept, if I plug in 0 for the x, I have 400, y equals 70,000. Divided by 400. Okay, I got 175 for my y-intercept. So at 0, 175, I'm just guessing about where that is. I have my y-intercept, and if I connect that, I get the boundary line. Okay, if this is less than or equal to, I don't switch the sign, so it should be lower than the blue line and lower than the pink line, and it should still say stay in quadrant 1, which means we're looking at this region down here. Okay, I'm trying to maximize the profit, so I need to find the vertices of this scenario. Now the first vertex is 0, 0. This is not going to give me my maximum unless my profit's 0. Okay, now my next vertex is 250, 0, which I labeled already because it was an intercept. And then 0, 175 is also already done because I found it as an intercept. So I just need to calculate this one right here, and then I'll have my last vertex. Okay, and how you solve for it, substitution, elimination. This is when your algebra comes into play. Okay, and I'm going to use a calculator. If I didn't use a calculator, I would probably try to cancel something out. See, I'm going to multiply the pink one by negative 250. Okay, y equals 50, so x plus y equals 250. Okay, so this point must be 200, 50, which seems reasonable, even though it's only a sketch. And you're going to show your work, showing where you got that intersection point just like I did. Okay, what am I trying to maximize? I'm trying to maximize my profit, which is the function I wrote right here. You are welcome to use your calculator to plug this in. Obviously, the profit's 0 when you sell 0. Okay, plug in 45 times 250 plus 50 times 0. If I give you numbers this terrible, I will also let you use a calculator. If I plug in 0, 175, I get 8750. And if I plug in 200, 50, I get 11,500. And I am trying to maximize my profit. Okay, so what's the question? Find the number of units that should be stocked to maximize the profit. Okay, it doesn't actually ask me what the profit is, even though it is in fact $11,500. So it asked me find the number of units that should be stocked. 200 units of the $250 model and 50 units of the $400 model. Should be stocked to maximize profit. Okay, so I answered the question. If they asked me what the profit would be, I would say, oh, the profit's going to be 11,500. Okay, this is like a bonus example. I'm not going to do this one in class. Okay, this says a dietitian is asked to design a special diet supplement with 2 different kinds of food. Each ounce of food X costs $3.50 and contains 20 units of calcium, 15 units of iron, and 10 units of vitamin B. Each ounce of food Y costs $2 and contains 10 units of calcium, 10 units of iron, and 20 units of vitamin B. The minimum daily requirements of the diet are 280 units of calcium, 160 units of iron, and 180 units of vitamin B. How many ounces of each food should be mixed to obtain optimal cost and meet the minimum daily requirements? Okay, so define the variables. What's it asking for? It's asking me how many ounces of each food. So X is going to be the ounces of, what's the food? Oh, food X. Now that's easy. Y will be the ounces of food Y. Okay, write the inequalities representing the constraints, and I am going to assume X and Y are greater or equal to 0, without writing it out explicitly. Okay, so what do they tell me that has a restraint? They tell me the minimum daily requirements. Okay, minimum daily requirements mean it must be this or higher, which means I'm talking about greater than or equal to. Okay, so first it tells me 280 units of calcium. So I'm going to go ahead and look for how much calcium. Blah, blah, blah. So food X has 20 units of calcium. And then food Y has 10 units of calcium. Then I'm going to go to my next restraint, 160 units of iron. So X is 15. And food Y has 10. Okay, and then what else? Vitamin B. So minimum daily requirement is 180 units of vitamin D. Food X has 10. Food Y has 20. Okay. Write the objective function. The objective function is the cost. Okay, so let me look. Where does it tell me the cost? Okay, food X costs $3.50. I'm going to use C. You could use Z. Some people like to use Z. 350X plus what is the cost for Y? Y is $2. Okay, because this is, you want to optimize your cost, you don't want to pay a lot of money, so we're looking for a minimum because it's a cost. If it asked me to optimize my profit, I would want a maximum because maximum is good. Profit is good, cost is bad, so I want my cost to be low. Okay, I'm going to sketch a graph. Okay, it's quadrant 1, so I'm only going to look at quadrant 1, and I'm going to use intercepts again. Okay, so if I want the x-intercept, I make this 0. So 20x equals 280. So x is 14, and I have no idea my scale, so I'm just labeling it. Okay, if I want my y-intercept, 10y equals 280, my y-intercept is 0.28. So let me put this higher. My graph doesn't have to be perfect, but I want it to be kind of reasonable so that I can tell where the vertices are. Okay, now for the second inequality, if I do 15x equals 160, I don't know what I get. I get x equals 10.66666666, which is good enough for my graph. Let's see, where is that? About here, 10.666666, comma 0. Okay, and then for my y-intercept, 10y equals 160, so y is 16, and I'm just going to guess about where 16 is relative to the other things. And I forgot to draw my line. Here's my blue line. Okay, and then for my red function, okay, 10x equals 180, so x is 18 for the y-intercept. 20y equals 180 tells me the y-intercept is 9, which is kind of low. Okay, now was I going above or below? Okay, these are all greater than or equal to. Am I dividing by a negative? No. If I plug in 0, 0, it doesn't work. So I'm shading above all of these lines. So if I'm above the red line, the purple line, and the blue line, where do I end up? Okay, so I'm ending up somewhere way out in this infinite land, which means it makes even more sense that I'm finding a minimum since this is not going to have a maximum because it's unbounded. Okay, now I'm going to check my vertices to see which one gives me a minimum cost. But first I have to find all the vertices. So one of them is 0.28, and I already labeled it because it was an intercept. Okay, another one is this 18.0. Okay, the third vertex is going to be this one right here. Now it's weirdly enough, this purple line did not affect my system at all. I could have left it off and it didn't change my results because it's not touching the shaded region. Okay, so let me see, red and purple. No, red and blue. 20x. I really don't like these big numbers. I'm going to divide off some of the big numbers. Okay, let me divide by 10 on everything just to make it nicer. You don't have to do this. If you have a calculator, you might not care. Okay, I got x equals 38 over 3. I still need y. Let me see which one looks nicer. I'll plug it in the blue equation. 2 times 38 over 3. That's 28 times 3. 84. 84 minus 76 is 8 over 3. So 38 over 3, comma 8 over 3. Okay, now what's it asking for me to do? Minimal cost. Okay, so I'm going to go ahead and plug each of these into my cost equation. You can use a calculator. And since it's money, rounding is a very reasonable thing to do. Okay, so this one looks like $56. Okay, 350 times 18 is 63. Okay, and then I'm putting 3.50 times 38 over 3 plus 2 times 8 over 3. And because it's money, I'm going to go ahead and decimal it and write down all the costs so I know you calculated each of them. Okay, what am I trying to do? Minimal cost. So the minimal cost is this one. And then what does the question ask? How many ounces of each food should be mixed to obtain optimal cost? So it doesn't ask me the amount, but I needed the amount in order to determine which one was minimal. So let me write the answer. Okay, so minimal cost with 38 over 3 ounces of food X and 8 over 3 ounces of food Y. It didn't ask me how much, but if it asked me, I would say $49.67.